Hello and welcome to this video. We're the presenter number 9 and this video we're gonna talk about testing the tensile strength of steel. So before we start, we want to see who this video is really for. Now, if you're designing a component from steel, it is imperative that you understand the yield strength and the ultimate tensile strength to ensure your final product meets all the design criteria, ensuring product safety. So for all aspiring engineers out there, this video will be quite useful for you in the future.
So let's have a look at tensile testing. So why is tensile strength so important? Knowing the tensile strength of a steel ensures the manufactured product is safe for use throughout its life expectancy. The result of selecting a steel with a lower tensile strength than the product is expected to experience can have disastrous consequences and potential fatalities.
Let us also define the tensile testing. What really is tensile testing? Tensile testing, also known as tension testing, is a fundamental material science and engineering test in which a sample is subjected to a controlled tension until failure. Properties that are directly measured via a tensile test are ultimate tensile strength, breaking strength, maximum elongation, and reduction in the area. From these measurements, the following properties can also be determined: the Young's modulus, Cuizon's ratio, yield strength, and strain hardening characteristics.
Now, let us proceed on how to check the tensile strength of steel. First is to prepare the sample pieces. Like for example, this test piece that has a cylindrical test region with an original diameter of 10 mm and an original gauge length of 100 mm. Within this test region, distance marks have been drawn at regular intervals. They help to visualize and measure the plastic behavior of the specimen.
Second is to load the specimen into tensile grips. Using a hand control, move the upper crosshead into its correct starting position. Now, we can place the threaded ends of the test piece in the lower and upper grips of the testing machine.
Then select the necessary testing parameters on the control computer.
Ready the test starts and carefully prepare the extensometer sensor arms to the test piece. This way, the gauge length can be measured throughout the whole tensile test. The gauge length is displayed at the bottom right corner of the screen. At the beginning, it amounts to 100 mm.
Begin the test by separating the tensile grips at a constant rate of speed. During the tensile test, the test piece is slowly and constantly elongated with a standardized speed. The force that the test piece opposes to the imposed elongation is recorded and can be seen at the bottom left-hand corner of the computer display. The material behavior can best be observed in the force elongation diagram. The force F is being plotted upwards on the vertical axis, the elongation delta L towards the right on the horizontal axis.
At first, the force rises rapidly. Force and elongation are proportional and form a steep straight line in the diagram. In this area, the material behaves elastically. If the test piece were to be unloaded from this area, it would be spring back completely to its original length.
In materials with yield point phenomenon, the end of the elastic area can be seen clearly. The plastic deformation starts abruptly and is accompanied by a sudden drop of force. If the test piece were to be unloaded now, it would not spring back to the original length, but instead show a permanent elongation.
In the next stage of the tensile test, an almost constant force level with slight fluctuation occurs. This phenomenon is called the Lodos effect. After a certain strain, known as the loader strain, the force increases again. The material opposes an increasing force against the imposed elongation. It strains hardens.
Up to the point of maximum force, the test piece is strained uniformly along its length. This means that the test piece gets longer and thinner but keeps a cylindrical shape.
As soon as the maximum force is reached, a neck begins to form at one point of the test piece. All further plastic deformation now only takes place at the neck, and eventually the test piece fractures there. And the test after the sample breaks.
The test machine will then be able to produce a report showing the technical data. The next step would then to analyze this report.
In the recorded force elongation diagram, the force FAH at the upper yield point can clearly be seen. This is the highest force the test piece can sustain elastically. FAL is defined as the force at the lower yield point. Fmax as the maximum force. Using these forces, strength properties of materials can be calculated. The upper yield strength RAH is calculated by dividing the force FAH by the original cross-sectional area S0. The lower yield strength RAL is defined in a similar way. The maximum force divided by the original cross-sectional area is called tensile strength Rm.
In the last step, the tester swings the extensometer back into its resting position and removes the broken test piece. On the work table, he puts the fragments back together again. With the help of the distance marks, the percentage elongation after fracture can be determined. This is the permanent strain after fracture and amounts to about 30% in this example. Please note that the elongation after fracture depends on the length of diameter ratio. By measuring the smallest diameter at the point of fracture, the percentage reduction of area can be calculated. It describes the reduction of cross-sectional area at the point of fracture in relation to the original cross-sectional area.
So that's all about testing the tensile strength of steel. We hope that you have learned something on this video. Thanks for watching.